Hello and welcome to this presentation. My name is Edson Shivuri, and along with my partner Hendricks, we will be taking you through the EasyMQTT system, an IoT API for creators by creators. So to start things off, Jet will be giving you a brief overview of the IoT space we'll be working in, as well as a description of the hardware we have used. I will then proceed to describe an overview of the API, and then both me and Jet will give brief descriptions of certain key parts of the API, after which we will give a brief demonstration, as well as some final thoughts and conclusions.
Our API will be operating in the smart home and automation IoT space, whilst the demonstrator will be focusing in on a smaller subset of this, home security, whilst touching on automation, and this is to show the wide range of functionality that our app covers, as in the demonstrator it will be interfacing with alarms, sensors and locks. But it's important to highlight how wide the space is, and that's why we wanted to make our API as modular, user-friendly and easily configurable as possible. When it came to choosing a hardware module in this IoT space, we had many constraints that we needed to consider, but the most important and determining factors was that the board needed to be easily programmable, have a suitable number of pins for use, and these pins needed to be able to interface with the common protocols, such as SPI, I2C, and UART. This led us to the ESP family of boards, and two members of this family specifically, the A266 and the 32. The 32, while being bigger, faster, and having more memory, is also more expensive, and this processing power was not necessary in our design, where low power is as important as possible in the IoT space. Also, it meant that if we could get the API running on the ESP8266, it would be a lot easier to port upwards.
Our EasyMQTT API serves to simplify the creation of IoT systems by abstracting all device setup and configuration, leaving the user to focus exclusively on the functionality that they would like to implement. Additionally, by using the complete system, even an inexperienced user can easily create powerful IoT systems that can be used for monitoring, control, as well as automation, both locally as well as remotely. This API consists of three key parts, namely the ESP device setup and configuration, which includes the flashing of the device. Secondly, the MongoDB configuration as well as REST API. And thirdly, we set up a broker which runs on a Raspberry Pi.
The main feature for the ESP8266 in our API is that we have abstracted the setup for the device to make it extremely simple for new users. It will also allow users to easily integrate the ESP into already existing projects. The way this is done is through a setup device file. It will prompt the user for a series of inputs, such as their broker IP address and their Wi-Fi credentials. Once the relevant information is inputted, the program will automatically generate the correct files to be copied over to your ESP. It will then flash your device with MicroPython and copy over the necessary files. Once this is done, your device is ready to use. You simply need to give it power. On its first boot, it will connect to the Wi-Fi and connect to the broker. It will send a message telling the broker that it is now registered. Then the device is ready to use. It can use any of the features included in our API. This is not limited to switching and toggling devices attached, reading from a variety of sensors through ADC or SPI, as well as digital reading, i.e. checking if the pin is a high or a low value. You can schedule a timer to automate tasks, and you can also schedule a listener, which will act as an interrupt to set off things such as alarms. The ESP also saves its states in a pin configuration file. This means that if the device fails for some reason, or if the user resets the device, it will load its most recent pin configuration on startup, so that your device saves its state.
The EasyMQTT API provides users with a Python Flask REST API that can be run on a local web server. This API essentially forms the communication bridge between the broker program running on the Raspberry Pi as well as the database running on MongoDB Cloud Atlas. Additionally, the IP address of our web server can be exposed to allow API calls from remote connections. And you will see this in the demonstration further, in the presentation further on, when we demonstrate our app integration. Additionally, The web server provides a liveness check system that allows users to be notified when the Pi has lost connection when they try to make a request. And finally, it provides data validation to ensure that all data in the database is kept in a uniform structure so that more advanced queries can be made by users.
To best describe how remote connectivity works in our API, we can start at the level of the ESP, which only uses local area network communication. It communicates with its broker on the same network using MQTT. All ESP devices on the local network will be attached to the same broker. This broker is then attached to the database and sends requests to the database using HTTP messages. The database, once it's updated or makes a change, will then notify all brokers of the change that was made. These brokers, knowing which devices are attached to them, will then redirect the messages to its intended target. This means that even though ESPs can only communicate with other ESPs on their local network using MQTT messages, the broker being connected to the database means that I can interact with devices not on my local network, as long as that broker is also attached to the database. This allows remote connectivity between devices, and allows remote connectivity between devices that were not set up together.
So if you see this current setup on the right hand side of the screen, you should be able to see that I have a relay connected to a door lock, and then my ESP device is over there, and connected to my relay is also a switch, right? And then on the left hand side of the screen, you should see an app running that can essentially control what's going on in the ESP device, right? And then also you'll be able to see the terminals for both the broker as well as the server. So what I'm going to do is I'm going to simply make a request. I'm going to say switches, right? So as you can see, it makes the get request over here, and then that comes in, okay? Then I will say, okay, well, I want to activate my door lock, which is now on my pin 5. I make the request.
Okay. So you've already seen id circuit. I've got my ESP set up to interface with his. So I've got my ESP attached to a magnetic door sensor. And when I open my door, it should send a message to his buzzer acting as an alarm to go off. Just fair warning, it may be a bit loud. 3, 2, 1, go.
Okay. In conclusion, the system that we have built can be used in whole or in part to speed up the development of IoT systems. Beyond that, it provides users with a useful monitoring tool in the form of a MongoDB database in conjunction with a Flask REST API. There are several major improvements that we plan to implement down the line, the two most notable of which are the addition of machine learning algorithms that can be able to find trends in data and automate tasks that are typically done in conjunction. And secondly, the addition of audio-visual capabilities to the system so that we can get live video and audio streams for certain monitoring applications. We hope you enjoyed this presentation, and thank you for watching.